Yes. All right. Welcome, everyone. This is trigonometry. My name is Professor Niazi. We'll be briefly going over the syllabus and then begin to discuss the first section that's on our to-do list. Okay, here's my contact information, course description, learning outcomes that you guys can take a look at. Our course materials is this textbook right here. That's what we'll be doing all our sections from and all of the problems out of. Okay, so make sure you have that because we'll be referencing everything out of that textbook. I have a YouTube channel and it has a lot of how-to on college algebra related stuff and trigonometry and calculus. If you'd like to reference that as a resource, by all means do so. Sometimes in my emails, I'll send links to specific things in those, and that should be helpful. Okay. Here's how your grades will be determined. 30% is your homework, 40% is your midterm exams, and 30% is your final comprehensive exam over everything in the semester. Okay. So I suggest to all of you that you start hitting the ground running in this class because everything in mathematics builds upon itself, okay? So make sure to hit the ground running. Treat this week as like it's finals week in terms of how hard you try. And your finals week will be a lot less stressful if you do that, okay? So now, there's other stuff here that you guys could be reading. Here's our schedule. This is tentative. It is subject to change, but this is kind of what we're going to be going to shoot. We're going to be shooting for this right here. So today we're going to be talking about the syllabus a little bit and then section 1.1. Okay,
Here's a statement about COVID-19, and that's about it. So let's get started. Actually, oh, I'm gonna need that back. Oh, well, actually, I don't need it. It's on the syllabus, so we could just turn that off. That's fine. I have a policy, as you can find on the syllabus. I do not allow technology. So I'm not okay with phones and other devices. Yeah, I'm just not cool with electronics.
My book is digital.
Is your book digital? Okay.
Sure.
And that's the only way you can access it?
Yes.
Okay.
It was only thing I could afford.
That's fine. That's fine. And you can access your textbook when the class is over. But during class, we'll be going straight out of the textbook. So it's as if you're having access to the textbook and more, because I have more knowledge to give you, and the textbook can't get you unstuck like I can, if that makes sense.
So we won't be using the book in class.
We will be using.
You'll be.
I'll be taking the place of that.
Okay.
I guarantee you it is worth your while. So what I expect is you guys to just take notes and ask questions when you don't understand. Raise your hand and say, could you explain that again? Like, can we do another problem like that? I would love to help you guys out. I would love to re-explain something. One thing I like to do is to explain one concept in a multitude of different ways, because when you do that, students tend to learn it. Maybe they don't get the first way and you change the way you formulate it, and then maybe that doesn't make sense, then you change the way you formulate it. Maybe the third way or the fourth way will make sense. But I will explain it over and over again as much as I can, given the amount of time that it's allotted, to help you learn. I really want each and every one of you to be successful in here. That's my goal, is to be the best instructor possible for you, to explain things as clearly as I can for you. And on top of that, give you an appreciation for mathematics and for science, to teach you all the cool things about it that your other teachers may have glossed over, okay? So it may be, it may make you kind of nervous that, hey, I don't have the book right now, but that's fine. Don't worry about it, okay? And another option is, if you would like, prior to class, you can print off the sections. That might help, but I unfortunately do not allow technology, because it, in my years of experience, can be distracting to students, okay?
I get that.
Yeah, that's all. Okay, so let's see, let me get a piece of chalk here. Let's talk about section 1.1, all right? Angles and special triangles. What I'm trying to tell you is I'm way better than the book, okay? Because you can't raise your hand to the book and say, explain that. What you see is what you get with the book, right? But with me, I'm a human being. I can answer and explain in different ways. So utilize me as a resource as much as possible, okay? And when I say I don't allow technology, that means I don't want to see it either. So if everybody could put their phones and other tablets and stuff like that away, I would greatly appreciate that. Thank you very much. That doesn't mean I want to deprive you of the outside world. If you have an important text message or phone call that you need to address, by all means, get up and go do that outside and then come right back. All right, that's fine by me, but just not in class. If you could respect that, that'd be great. Wonderful. Let's talk about angles. All right. In mathematics, and specifically the study of trigonometry, which trig has triangle in it, you guys will see that we're very interested in studying angles, okay? So to define an angle, first we have to lay the groundwork, okay? We'll define something called a point. Let's call this a point P. A point is just a dot in two-dimensional space. It's just on a flat surface, a point P. And now, actually, I want to call it a point V, okay? And you'll see why I want to call it that later in the very near future. So we have a point V, and then we can define something called array. R-A-Y, array. These terms aren't super important, but they just kind of lay the framework here. Array is just a straight line emanating from a point that goes off into infinity, just forever. It goes off forever. Okay. So let's say we have two rays emanating out of a mutual point V. Okay. We construct these two entities here. This leads us to the concept of an angle. An angle is a measured quantity that lies in between two rays. Okay? We typically denote our angles with Greek letters like theta or alpha or beta. Okay? So, in trigonometry, so far, we like studying angles. Angles can vary, right? These aren't concepts that are new to you. Everybody in here has an idea of what an angle is. Everybody in here has thought of this concept before, because these concepts are just natural to human beings. Okay? Now, I'm sure you guys have seen this kind of information before. So what kind of angle is this angle? Say what? A right angle. You are right. That means this measured quantity is at what value? 90. Yes, 90 degrees. What is this degree talk here? 90 degrees. What does degrees even mean, right? Who here wonders what a degree means? Degrees are just measurements of angles, and we quantify degrees by where they stand on a circle. So here, if you don't move at all, we say that you're at 0 degrees. Here, if you move halfway, for example, we say that you're at 45 degrees. Here, as this young lady noted, if you are perpendicular to the line, you're at 90 degrees, right? If you go all the way over here, you're at 180 degrees. If you go down here, you're at 270 degrees. And if you return all the way back to your same spot, you're at 360 degrees, right? Full rotation. I think they gave me this classroom on purpose, because usually when I talk about 360 degrees, I do a 360 roundhouse kick. But I'm really cramped unless I put that thing up and scoot the table aside. I'll give you a 360 roundhouse kick when we talk about angular momentum and angular speed, okay? I'll just go out into the halls and I'll do one about that, all right? I'm not kidding. I'm not kidding at all. It's an excellent time to show people what a 360 roundhouse kick is when you get to talk about it in class, you know? All right? What kind of an angle is this angle? Yeah, it's an acute angle. So when our theta, which we will commonly refer to angles as our theta, here it was 90 degrees. An acute angle theta, what can we say about it? 60 degrees is an example of an acute angle.
Less than 90.
Less than 90. I want to say it's less than 90. How less than 90 can it get? Forever less than 90? Till 0. Ah. Mathematicians are like this. If you say something, then we want more detail. And then you give more detail, then we want more detail. Then you give more detail, then we want more detail. This is how we are. This is an acute angle. Okay. This is terminology you guys are probably familiar with. Probably learned it at some point in your life. What about this kind of angle? Obtuse. I don't even know how to spell that. Obtuse. A-B-T-U-S-E. Is that how you spell it?
I think they use O. Is it an
Oh, it's an O?
A?
Why do we say obtuse then?
It's the English language.
Oh,
It
okay.
makes sense.
I see. I see. Okay. Obtuse. Obtuse. What quantifies an obtuse angle?
Anything over 90.
Anything over 90. Are you sure?
Pretty sure.
Can it surpass 180 degrees? I agree with you that it has to be over 90.
I'd assume it has to be under 180.
Aha! Correct. Because what happens if it ends up equaling 180?
It's a straight line.
Is there any angles there? There's no angles there. It's just a straight line. So you have to restrict it to greater than 90 or less than 180, or else the angle goes away. It's no longer an angle. So to define it properly, we set that inequality. That make sense? Okay, very good. More definitions. Definitions are like the letters of the mathematical language. You're learning to speak a new language here, the language of mathematics. So we're kind of defining new ideas. I mean, these kind of are some old ideas you probably already know, but we're defining more and more ideas here. Don't worry, it gets better. It gets a lot better. Okay. Now, let's talk about complementary angles and supplementary angles. Complementary angles. Two angles are said to be complementary angles. Two angles, alpha and beta, are said to be complementary if they satisfy this condition. So, for example, 30 degrees and 60 degrees add up to 90 degrees, don't they? So 30 and 60 are complementary angles. We could say this is our alpha and this is our beta, for example. Who here can come up with another example of two angles that are complementary? 90 and 90? You'd be close if you said 90 and 0, right? Right? Because if you say 90 degrees plus 0 degrees, it adds up to 90 degrees then. So 90 and 0 are complementary. Give me another example.
45, 45.
Yes. 45 and 45 are complementary. Why?
45, 90.
Yeah. There you go. Does that make sense? So to really understand the concept, invent one. Invent one. Okay? So for yourself, if you didn't answer in class, invent two complementary or invent two angles that add up to 90, and you would have invented complementary angles. Okay? They're going to look like this because notice that when you add them, they'll form a right angle. So now let's talk about supplementary angles. these angles are such that what do you think alpha plus beta equal here? Yes. Correct. So two angles are supplementary angles if when you add them together, they equal 180 degrees. Who here can come up with an example of two supplementary angles? Say that again?
120 plus 40.
Yeah, 120 plus 40. Notice this equals 1.
Oh, my bad.
Oh,
Okay, sure.
say what?
I came up short.
Came up short. So that's not supplementary, right? That's okay. 60 works because they add up to what? There's nothing wrong with what just happened here. You had a guess, it didn't work. You had another guess, that worked. That is exactly how you learn. You make mistakes and you learn from them. That's how learning happens. The more mistakes you make, if you work hard to learn from those mistakes, the more you can learn. Easy as that. I put that if because we all know people who constantly make mistakes and never learn from them, right? Who here knows people like that? That's not good. You have to, if you make the mistake, consciously work hard to learn from it or learn from it. Then and only then will you improve. Okay? Things you learn in math class translate to more than just mathematics. Can someone give me one more example of a supplementary angle?
105 or 75.
Oh, that's a good one. 105 plus 75, because this adds up to 180, right? So there you go. You have made this definition your own because you came up with an example of some supplementary angles. Okay? Good. Don't worry, it gets better than this. Although this is really fun too, right? It gets way better than this. We're just laying the groundwork down. Next, let's talk about coterminal angles. Okay, so prior to discussing this concept, let's talk about the concept of rotations. Okay. Let's say you have, a point and a ray. Okay. Let's say the yellow signifies what happens when I pick it up and rotate it about the fixed point P or the fixed point V. I'm going to call it V because V stands for vertex. The vertex is a fancy mathematical term that we utilize to indicate the point where two rays meet, the corner, if you will, the point, the part where you don't want your head to hit because it'll slice your head open, the sharp, jagged peak. All right. So we pick up this ray and we rotate it and we put it back down. So we rotated it through some angle, right? It's the same ray. We picked it up and we moved it and we put it down. Okay? This forms some angle. A coterminal angle is an angle that lands, that determines, so this is the initial leg. I should actually define this as the initial leg. then this would be what we call the terminal leg. Because the process of rotation has been terminated. We're done. We're done rotating for now. The first rotation has been terminated, and we rotated through theta degrees. A coterminal angle, you can almost guess it by the definition. A coterminal angle is an angle such that if an angle beta, do you guys see the orange? Let me see if the Zoom video looks like you can see the orange. I've been told orange is hard to see on there. So cannot take a blind eye to the feedback. And I would be darned if a piece of chalk prevents my students from learning. So maybe not that one. Green is not good, red's not good. I'm just gonna have to utilize yellow here. Beta, another angle, is coterminal to the angle theta. If their terminal leg is at the same spot. So notice, what if I were to rotate like this? If this was a rotation here, designated by an arrow like so, what if I rotated like this? Notice that it would run right on top of itself, wouldn't it? What does this mean? It means, man, I'm about to do a 360 right. I'll stick right here, maybe. All right, I'll just do it right now since we got that figured out right there. It means if I'm facing you here, I'm gonna push this over. It means that if I'm facing you like this and I do a full rotation like this, I'm still facing you, right? That's the same thing as a coterminal angle, right? So same thing. Tell me how many degrees do I rotate here? Because it's not 360 degrees. It's something different. All right? Ah! There goes my glasses. I always forget to take them off. I should wear contact lenses on those days. How many degrees did I rotate? Because when I was done, I was still facing you guys, wasn't I? It was 360? It was a little more. How many degrees was it? More than 360? But I ended up facing you still, right? So it was more than 360, but I still landed in the same spot. Well, what can we say about that? Facing you, I spun again, facing you. That's more than 360. But what is it? 2 360s, right? It's a double turn. The first one is a fake. It's a fake front kick. Make your opponent be like, whoa. It's always fun when you could do that in math class. People tend to get more focused into the lecture afterwards, okay? So notice that you can land in the same spot if you go 360 degrees, but you can also land in the same spot if after you go 360 degrees, you go another 360 degrees. What does this mean? Does this mean that I can go as many 360 degrees turns as I want and still land in the same spot? An infinite amount of 360 degrees will land me in the same spot? Yes. That's the whole point of all that demonstration. So, now that we've got that cleared, let's say this is our initial leg here. Let's say we rotate it through an angle of 45 degrees. Find, if this is our theta, find a coterminal angle alpha that lands in the same spot as the 45 degrees. So rotations in the counterclockwise direction, if you rotate like this, those are like adding positive degrees. Okay, so we want to add something to 45 degrees so that it would represent a different rotation, but one that lands in the same spot. Because this was a rotation here to go to 45 degrees. What is a rotation that I could have taken this initial leg to land in the same terminal leg as the 45 degrees? Say what?
315.
Close. That's a very close, because what you're doing is you got 360, you subtracted 45. That would be correct if I rotated the other way. I've not talked about that yet. But rotations that are counterclockwise rotations imply that you add degrees. Clockwise rotations imply that you subtract degrees. Say what?
405.
So notice that this is in the counterclockwise direction. So
are we just adding 360 to 45?
yes, and you want to know what? Maybe that is why you got confused. Okay. So yes, 360 plus 45. This is our coterminal angle beta, because it will land in the same spot, right? I feel like I led you astray by having this start off from here. Truly, I should have had it start off from here, but I'll make amends, okay? If you start off from here, it's as if you add 360 to 45. If you start off from here, it's like 360 to 45. If you start off from here, it's just like your 45 degrees is your new zero, and you just went 360 degrees. There's subtle differences that will make more sense later on in the class. This allows us to segue onto Y and X coordinate systems. So in trigonometry, it's pretty standard to utilize the Cartesian coordinate system, the X and the Y plane. Okay. So our initial leg is always this leg right here. And then we rotate it through some angle. And it goes over here. And this is the terminal leg. Okay. So here's another question to you. What if this is equal to 60 degrees? Can you find a coterminal angle to theta, which is equal to 60 degrees? Find a positive coterminal angle to it. 30?
No, never mind, sorry, I was thinking about a different thing.
Say what?
So it would be 60 plus 360?
Yes.
420.
Yes. So that's because if you start off here, you rotate one revolution of a circle, and you come over here, you land in the same spot. So the degree 420 degrees and the degree 60 degrees are coterminal. Does that make sense?
Yeah.
Okay. We'll do one more example. So those are positive coterminal angles. Don't forget that this is rotating counterclockwise is adding degrees. Rotating clockwise is subtracting degrees. Okay. So with that knowledge here, let's say I'm here at, let's say I'm here, and this is the angle 20 degrees. Find a negative coterminal angle to 20 degrees. Meaning, instead of rotating like this, rotate like this. Go clockwise.
So it'd be like 340? Because you're subtracting. Or would you subtract the 20 minus 340?
It's not 340.
Is it
Or
negative
360, I mean,
340?
sorry.
Yes, 360. What is that, sir?
Negative 340?
Yes. Negative 340 degrees.
I'm lost. Where do we get 340 from?
I will explain that for you in a second. Okay, I'll put a negative here. I'm glad that you said that. So this all stems from the fact that when you rotate like this, counterclockwise, this implies positive degree change. And if you go in a full circle, that means we add a positive 360. Okay, but if you go like this, like we're doing here, clockwise, this implies a negative degrees. And if you go counterclockwise, or if you go clockwise in a full circle, that will give you negative degrees. So full circle here is adding a positive 360 to whatever value you have. And over here, this is subtracting a 360 from whatever angle that you have. So because we're going clockwise, we got our initial angle and we subtracted 360 from it to get negative 340. If we went the other way, instead of going like this, we went like this. We would get a positive coterminal angle to 20. And then we would get 20 degrees plus what?
36.
Yes. This minus is there for clockwise rotation. This plus is here for counterclockwise rotation. Rotating counterclockwise in a full circle is tantamount to adding 360 degrees to whatever angle you have, which will produce a positive coterminal angle. Rotating clockwise is tantamount to, in a full circle that is tantamount to subtracting 360 degrees from whatever angle you have. So notice, what does 20 plus 360 give us? 380 degrees. So both negative 340 and positive 380, these are both coterminal to what angle? Yes, 20 degrees. They're both coterminal to 20 degrees. Does that make sense? They both, when you pick it up and rotate it, land in the same spot. Notice that we can actually add or subtract any integer multiple of 360 degrees and still get a coterminal angle. So what's rotating twice? How many degrees? What's 360 plus 360? 720, like my roundhouse kick. So 20 degrees plus 720, which is equal to 740. This is also coterminal to 20 degrees. Because that's just 2 times 360. This is what I mean by integer multiple. Any whole number multiple of 360 degrees, 2 times 360 degrees, 7 times 360 degrees, 5,641 times 360 degrees. They will all provide coterminal angles to whatever you're adding them to. Okay. Another thing to take away is that rotating counterclockwise is the same thing as adding degrees. And rotating clockwise is the same thing as subtracting degrees. That's one thing that definitely needs to be remembered. That will show up over and over again. Why do we do that? Why isn't this positive and that negative? Well, it's because you have to pick, you know. You have to choose one to be positive and one to be negative, or else you wouldn't be able to have one be distinct to the other. So in the historical formulations of the subject, the mathematicians gathered around and they decided, hey, let's just say counterclockwise is like adding and clockwise is like subtracting. One way to remember it is that the clock subtracts time away from your life. I just came up with that right now. I'm going to remember that one for the next generation of trig students. Oh, next topic, converting between decimal degrees and degrees, minute, and seconds. All right, so when we talk about degrees, we talked about a circle, right? We get a circle, it's like a pizza, and you chop it up. If you chopped up the circle in 4 pieces, then the only way you can measure any angle is in terms of these 4 pieces. But that's too rigid, right? We want to have a more fine measure. So we chopped it up into 360 pieces. Chop up a circle into 360 pieces. So each of the slices are 360. So here's 0, 90, 180, 270, okay? So in order to chop up the pizza in a more fine way, I mean, I'd be pretty mad if someone offered me a degree slice of pizza. That's pretty, it's just like a pizza noodle. You know what I mean? I'd want, you know, like 90 degrees of pizza, or maybe like 180, or you know what, just give me 360 degrees of that pizza and go away. Right? The 360 degrees of pizza would be the whole pizza. 90 degrees of the pizza would give you 1 slice here. 180 degrees would give you 2 slices. But you know what? We chopped up the circle into smaller and smaller values because we wanted to be able to measure smaller and smaller angles theta. Okay? So here's the thing. Degrees is not the smallest we can go. We can go into something even smaller. Okay? What do I mean by that? Well, in 1 meter, how many centimeters do you have? 100, like a century centimeters. So that in here, stuffed in 1 meter, there's 100 centimeters. All right? But in the same thing, how many millimeters do you have? 1,000. It's the same amount of length. It's a meter, but a centimeter, you have 100 of them, and a millimeter, you have 1,000 of them. Clearly, 1 millimeter is smaller than 1 centimeter. And 1 centimeter is smaller than 1 meter. So meters are analogous to degrees. Let's chop them up finer. What is the analog of the centimeter? Minutes. Minutes. So we have degrees, minutes, and guess what? To kind of go along with the time analogy, let's do seconds. Where this kind of correlates to the millimeter idea. This kind of correlates to the centimeter idea. And as you figured out, degrees correlates to the meter idea. How many minutes in an hour? 60. Yes. And so there's 60 minutes in 1 degree. Because degree is and also now here analogous to 1 hour. If you want to think about it in terms of a clock. Okay. So 60 minutes in 1 hour, which is the same thing as 60 minutes in 1 degree. So how many minutes or how many seconds? How many seconds are in a minute? All right. So we have these equations here. So to reduce the clutter, let's talk about these equations. Okay, so we have 1 degree equals 60 minutes. And we have 60 seconds equal 1 minute. These are the equations we have to deal with. Okay? So, here's your assignment for right now. Convert 123 degrees, 0.15 into degrees, minutes, and seconds. So it's like a decimal degree. How do we convert a decimal degree into degrees, minutes, and seconds? So we're going to remove the decimal. We're going to make it precise. So what we do is we say, okay, this whole number part, that's just what we call, this is degrees, right? Done. We got the degree part. Done. Now let's analyze that decimal part, that 0.150 part. This is still a 0.150 degrees, right? Why am I saying this? I'm saying this because this is the same thing as is it not? Right? Those are the same things. So since this is in degrees and it can't get any smaller, let's just make the decimal part smaller. Define it in smaller quantities in minutes and in seconds. So let's set up a proportion. We know in 1 degree, how many minutes are there?
6.
Yes. So notice that the degrees here, boom, and here, boom, cancel. So we can figure out how many minutes is 0.15 degrees by utilizing a calculator. I would say a calculator is the only device that I would allow you to bring. Your phone doesn't count. Has to be an actual calculator, or else you'll get distracted, like a scientific calculator. So 0.15 times 60. Say what? I heard someone whisper it.
It's 9.
Yeah. 9. I think it was 9 minutes. Does everybody get why I did this here? And so the units cancel.
I didn't know you could do that.
Yes. Here's why. What's 10 divided by 2? You just knew that right off the bat, didn't you?
Yes.
But notice that that's the same thing as 2 times 5 divided by 2, right?
Mhm.
So we reduce to a 5 because what happens? These cancel. What do we mean by they cancel? Well, we mean that 2 goes into 2 once. So this is exactly the same thing as 1 times 5, which is just the same thing trivially as 5. That's exactly what we mean by they cancel. We mean in the numerator and in the denominator, we have the exact same thing. And they divide into each other to become 1. Anything divided by itself is 1. And so whenever you do that, they contract to canceling, and you just get what was left superfluously. Same thing here. This is 0.15 degrees divided by 1. So you're multiplying fractions. Numerator times numerator, denominator times denominator. 1 times 1 is 1. You could have just put that 1 down there. It's trivial. It's understood to be there. It doesn't change the expression. But it's secretly there all the time. And because the degrees canceled, just like the 2's canceled, the minutes is the only unit that remains, so it gets retained. So I'll just delete this because it's cluttery, right? 0 minutes. So can we go any further?
Yeah.
Well, not with the decimal that we've been given. We're actually done. There is no seconds. The seconds is 0 because there's nothing remaining here. Because the remainder was like a 0, and 0, or the remainder was like, so we could say 0.150 is the same thing as in degrees, 0.150 plus 0.000. Of course, right? This is true, but we can't convert nothing into something. So if we wanted to convert this piece into seconds, there's nothing to convert. So it's really 0 seconds. This will make more sense when I do more examples here. But we're done. We converted it into degrees, minutes, and seconds, but the seconds are 0. So this is the same thing as 123 degrees and 9 seconds. Just like degrees gets a special superscript, minutes gets this thing, and seconds gets 1 second is equal to this.
You said seconds, is that 9 minutes or 9 seconds?
9 minutes, sir.
Okay.
Yep. So I could have written this like this. Just new terminology that I had not introduced. Basically, this is showing you that you can convert a decimal degrees into smaller and smaller pieces. Let's do some more examples, and it will make more sense. Let's do 142.2075. What did I say again? 0.2075. All right. Convert this to degrees, minutes, and seconds. I'm gonna need some more space here. So there is sort of an algorithm to doing these problems. The step one of the algorithm is to get the whole number part and just kind of put it to the side so we're not confused. Here's what I mean by that. This is the same thing as this. Is it not? Is it not? It's the same thing, right? Okay. So you're not going to throw tomatoes at me if I write that. Okay? Now, we say this is already a whole numbers in degrees. We just ignore it. Now let's talk about this guy. Let's make that into a smaller and smaller quantity. So we know in 1 degree, how many minutes do we have? Very good. 60. And I won't put minutes anymore. I'll just put that symbol right there. So notice the degrees cancel. So to know how many minutes this is, it's the same thing as multiplying 60 times 0.2075. And that gives us 12.45.
So we just put the 12 minutes aside and then do we write down the,
Yeah,
okay.
that's right. The algorithm continues. We bring this down here, and we say that this is equal to 12 minutes plus 0.45 minutes. Yeah,
So we're looking for whole numbers, basically.
that's right. That's right. So then we break this down here and we come to here. So then this is what we want to analyze now. So we'll bring this down because we know that it ends up equaling. So right here, we'll put 0.45 minutes. In 1 minute, how many seconds do we have? 60 seconds. So we notice we have that there. So notice these units cancel. So to figure out how many seconds I have, I just merely multiply 0.45 times 60.
27
Very good. 27 what?
seconds.
Bam, bam. So our final answer will be that this quantity is equal to 142 degrees, 12 minutes, and 27 seconds. See what I did there? Every time I broke up the whole part and the fraction part, the whole part remained. Whole part remained. And then here, this is the last step. We turn the fraction of the last one to a whole part of the second one. It's a tiered system. Okay. Let's do let's do the reverse. What do I mean by reverse? I mean, given degrees, minutes, and seconds converts to decimal degrees. So what about 60 degrees, 18 minutes, and 45 seconds? I mean, 61 degrees, 18 seconds, and 45 seconds. Convert this to decimal degrees. Well, the 61 just stays 61, right? We just ignore that because it's already in degrees. It's the minutes and the seconds that we need to now convert to degrees, right? Okay. So let's start off with this one. The first one we got to convert. We can say 18 minutes. I want to convert it down the line to become degrees, right? So down here in this denominator, the units need to cancel with this. So the units need to be what here?
60 minutes.
Yeah, that's right. In one what? Yeah, very good. Cancel those out. So to find out the degrees, it's the same thing as getting 18 and dividing it by 60. 0.3. Boom. We just converted 18 minutes to 0.3 degrees. Let's do the other one. What about 45 seconds? The denominator needs to have seconds to cancel. So what can I stuff here and what can I stuff here?
60 seconds.
60 seconds in one what?
Degrees.
1 minute.
1 minute.
In 1 minute, right? In 1 minute. Can't jump all the way to degrees. That's where we eventually want to land. But first we have to go through the minutes first, right? The minutes come first, then the degrees. So these cancel. And then we can just automatically say, in 1 degree, how many minutes do I have? Huh? 60 what? Yeah. Cancel, cancel. So now your answer is going to be in degrees. It's merely multiplying 45 by 1 and 1, which is trivial. So you just get 45 divided by 60 times 60. So the result is get 45 divided by 60 times 60, which is 45 divided by 3,600. Zero point 0125 degrees. Okay, so we want it in decimal degrees. We're almost done, right? We have to get 61 degrees, add it to this contribution, 0.3 degrees, and add it to that contribution, 0.0125 degrees. So we end up in a decimal degree, just 61.3125 degrees. I told you I'm better in the book. You gotta trust me on this one, man. You guys can bring calculators, but that's it. No technology. It's gonna hamper your learning. I want to augment your learning. People are too dependent on technology these days. I'm kind of old-fashioned. Next, let's talk about special triangles. Well, what do we mean by special triangles? Well, there's a right triangle. You guys familiar with a right triangle? One of its angles is 90 degrees. Notice that the other angle here can be like a 30 degrees and a 60 degrees. It doesn't have to, but this is one of our special triangles. We call it a 30, 60, 90 triangle. Also called a right triangle. We also denote this as right triangle. There's another kind of special triangle here. And this is a triangle that has the same angle for each angle. What am I doing here? What am I doing here? I mean this to be, I put too many 45s here. And I drew the triangle wrong. Here we go. Another version of the right triangle. There you go. Is this version. What I drew up there earlier is not a triangle. And actually here, this is an important thing to talk about. When I drew up here, I wrote this. I wrote this. Please tell me, somebody, why is that not a triangle? Yes. 45 plus 45 plus 45 does not equal 180. And to be a triangle, the sum of your interior angles has to equal 180, right? Yeah, that's only in flat space. In curved space, it's no longer true. You can have positively curved space and negatively curved space, like in the regions near a black hole. So triangles near a black hole, the sum of their interior angles does not equal 180 degrees. But that won't be on the test. That's just kind of cool. That just goes to show you that the mathematics we're doing here is just, at the end of the day, just the tip of the iceberg of reality. So then we have a 45, 45, 90 triangle. Okay. We got the 30, 60, 90. 45, 45, 90. Those are all the ones they want for you to call special here. Okay. So notice that these are indeed flat Euclidean triangles. These triangles are near a black hole. And so the sum of their interior angles equals 180 degrees. Notice 90 plus 60 plus 30 is equal to 180. 45 plus 45 plus 90 is equal to 180. We have bona fide triangles, okay? What's so special about these triangles? Well, remember, for an arbitrary right triangle, what is that theorem everybody knows about triangles? If I call this C, A, and B. Yeah, say it, say it.
Pythagorean Theorem.
Yes, but what does it say?
X squared equals.
Yes, it's called the Pythagorean Theorem, but Pythagoras stole it. So it shouldn't be called the Pythagorean Theorem. It should be called the Pythagoras' students who he stole it from theorem. You gotta make thieves, you gotta throw shade on the thieves, you know? He clearly stole it from one of his students in his geometry academy. Yeah, I know. That's how it goes though. I gotta undo all that though. He didn't know I was gonna be born and reveal that stuff. Very few people know that. People in the mathematical community know that. Actually, not all of them. Anyways, this is true. For any right triangle, that is true, right? Okay. So what if I put an A and a B and a C here? Then A squared plus B squared is equal to C squared, right? But what can we say about A and B? A A and B are related in a very special way in this situation here.
Complementary.
That's true. They are complementary angles. That's not what I'm looking for, but that is a true statement. What I'm looking for is that they're the same value. How can we know this? Well, when we open up an angle, what happens to that leg at the end of it the more and more we open up the angle? More and more I open up that angle, that leg that connects it. Here's a small angle, leg that connects it. Larger angle, leg that connects it. I'll call this L, I'll call this capital L. Call this theta 1, I'll call this theta 2. Where theta 1 is less than theta 2. What can we say about little l and big L?
Little L is less than big L.
Yes. Yeah. So we now realize that increasing an angle ends up doing this phenomenon. It increases the length of this leg. If I increase it more and more, this leg gets longer and longer. If I decrease it more and more, this leg gets smaller and smaller, right? So your angle dictates how long the opposite leg will be. Is that not what we've realized here? So take a look. This is 45 degrees, its opposite leg is B. This is 45 degrees, its opposite leg is A. Although it's not drawn to scale, because, you know, I'm not Pablo Picasso out here. If I perfectly drew it to scale, this leg should look as long as that leg. I didn't do a good job of that, but, you know. That's where technology beats me. Technology makes good shapes. But now you can believe that that's true, right? That they're the same. So, if they indeed are the same, notice what happens to the Pythagorean Theorem, which stated this is true. But if A is equal to B, then we'll just replace B and express everything in terms of A. What's the point? Oh, well, it's because we can actually find something new here. A squared plus A squared is 2 of itself. Right? So, you guys have all taken pre-calc. What happens when I take the square root of both sides? What happens to the right side when I take the square root? Yeah, technically plus or minus C, but we'll just call it C because we'll take the principal square root. What happens to the left side? The square root travels across multiplication and division. But it does not travel across addition and subtraction. So since it does travel across multiplication, we get this. But square root of A squared is what? Yes, sir. So we get this. That's a special relationship unique to this special triangle 45, 45, 90. Right? It's unique to that kind of a triangle. So, given a 45, 45, 90 triangle, this implies that this is true. Okay? But notice, because A is equal to B, I could replace that with a B as well. So you get another equation for free. It's a buy one, get one free. Because A and B are the same, I could have just rewrote it as that. Now let's talk about this one. All right, what can we say about the 30, 60, 90 triangle?
A and B aren't labeled one.
They're not, because what their opposite angles are,
They're not the,
they're not the same. Which one is going to be bigger, A or B? A is going to be larger than B, right? So this whole thing we did here doesn't work. But we can still say that A squared plus B squared is equal to C squared. Unfortunately, class time is over. So during next class, I will show you how we can get some rules for this kind of a special right triangle. I will upload your homework assignment onto the Canvas page. You have a week to do section 1.1 homework. And yeah, now you're free to get on your computers and phones and whatnot. Hopefully you didn't have too much withdrawals.